Have you ever felt like you just aren't good at something? Or felt weird, that you're not like the others around you? Well, that's how one of the dinosaurs feels in Hold Your Head High, a new book all about learning what makes you you. Marge is a young Amargasaurus, a sauropod who's left home to go adventuring, accompanied by her friend Vincent, the Vincellestes. Not far into their travels, they start meeting other sauropods, but they look nothing like Marge. They can eat from the tops of trees rather than the underbrush. These other sauropods are all big and strong, or tall and graceful. Marge is small and hunchbacked. She starts wondering if there's something wrong with how she's built, or if she looks weird, feeling like she doesn't fit in. She talks to her friend, Vincent. With his help, Marge works to figure out why she's built the way she is. I like this book because it teaches you that the traits that make you different from others aren't weird or bad. In fact, they might be just perfect for what you're good at. So no matter how tall or short you are, stretch your muscles really good, then run down to your local library to check it out today.
So here we have an Amargasaurus that a supporter of ours sent in. I am told it is an Amargasaurus, even though aside from the spines on the neck, I wouldn't be able to determine that because they've just portrayed it as a already quite wrong and quite stylized sauropod and then just stuck spines on it, which is not an uncommon approach to restoring Amargasaurus. Whereas this toy at least is making an effort. I applaud this toy for its overall approach to restoring this animal as a dicraeosaurid. These were relatives of animals like Brontosaurus or Diplodocus, but they took a different path. They had short necks, they were medium to low browsers, and they were pretty small by sauropod standards. So if we want to try to reconstruct what these famous neck spines of Amargasaurus looked like in life, we should consider why did they grow neck spines in the first place? Was it tied to their lifestyle? What advantage did the spikes confer if the animal was always having its head down near the ground? We've known about Amargasaurus for just under 30 years. The description was in 1991 by Salgado and Bonaparte. José Bonaparte is a paleontologist we've met before. We only just lost him. May he rest in peace. But a very prolific Argentine paleontologist who we've seen before in our Carnotaurus episode. The 1984 expedition that brought back Amargasaurus is also the same expedition that brought back Carnotaurus, even though Carnotaurus is from much younger rock. Amargasaurus, as the name would imply, is from La Amarga Formation, which is Barremian through Aptian in age, so it's right around 125 million years ago, early Cretaceous. If we translated its name literally, it would mean bitter reptile, but I don't think we need to go that far because we have Amargastegos from the same formation, which may or may not be valid. We have Amargasuchus, which is a crocodilian from the same formation. We have Amarga titanus, which is a larger dicraeosaurid from the same formation. There's a pattern to the naming of animals from this formation is what I'm getting at. So it just means from La Amarga. The specific name, cazaui, is for Luis Cazau, who is the geologist that directed the expedition, the 8th expedition to go recover fossils in Patagonia, to go look at the Amarga Formation. So without him, no Amargasaurus. But the skeleton itself was discovered by one Guillermo Rugier. It is a pretty complete skeleton, which is helpful since it's the only specimen of Amargasaurus we've found so far. There's most of the vertebral column, other than the tail. We have a bit of the head, which is super rare for a sauropod, and we have a decent amount of the limb bones, though we're missing the hands. I do wonder if it being a dicraeosaurid is why it's so complete. There's a kind of a trend with recovering animal remains that for really large animals like sauropods, you might find one limb bone or one vertebra. Whereas for dicraeosaurids, since they're, elephant-sized, though obviously longer, we find a bit more of them. It is, I keep calling them smaller sauropods, but if they were alive today, they would be one of the largest land animals. They are about 9 to 10 meters long, but right about elephant in weight, which means they are a bit smaller than Dicraeosaurus. The description of Amargasaurus is where we get the term dicraeosauridae, because that was when it became apparent, hey, there's a whole group of animals that look like this. And Amargasaurus, as far as I know right now, is very closely related to Dicraeosaurus. They're in what's called a polytomy, together with Brachytrachelopan, which I can never say right, but I think I did that time. Which is interesting, because we have a whole bunch of Dicraeosaurids from Patagonia, but Amargasaurus remains most closely related to a late Jurassic Dicraeosaurid from Africa. As I mentioned, the arms and legs are incompletely known. We have a handful of foot bones. Anyway, we don't have any of the hand bones. We would expect the hands to look like this, though. These look like your normal sort of semi-tubular, weight-bearing sauropod feet, where I like to compare it to a hoof, but a hoof made of flesh. And they have the right number of claws, which is 1 on the thumb there. They look a little big for the arms that they're attached to, but that's really my only criticism of the hands on this toy. These arms might seem short to you, but that's Dicraeosaurids for you. Once you're adapting to be leaning forward all the time, you don't need long arms relative to your legs. You don't need even like equality between the arms and legs. You need your front to be down further. I'm not sure that the shoulder blade should be so visible. Like, I was going to say, I don't think the shoulder blade should be that small, but I shouldn't be able to judge how big the shoulder blade is looking at it through the tissues. Like, there's muscles attached to the shoulder blade. There's no way you'd see the outline of it quite that clearly. The hind feet have the correct number of toes, which is 5. Wrong number of claws, though. These have claws on every toe, whereas as far as I know, these animals would have had 3. And the first 2 would be the largest. I do like that the arms are underneath the animal. They're right underneath the creature bearing its weight. Though the thorax looks a bit narrow. If you look at the width of the ribs and the wings on the front of the ilium, the upper hip bones, at least judging from museum mounts, this animal would be a lot rounder than this toy is. One thing I do like about the thorax is that it has these ridges up top. I don't know how reasonable it is to have them so visible. Like, I don't know if you would see the outlines of the individual spines on the vertebrae, but they did have really high spines, even on the parts of the vertebral column that aren't, the famous neck spines. That said, because they've gone into so much detail even through the flesh here, I can say I think they're forked a little too far back. I think that the last few vertebrae before you get to the hip were already solid. They wouldn't have that space in the middle. I can't say that it's completely unreasonable to have those ridges on the back visible through the flesh, but there are other interpretations you could do. You do occasionally see them with Czerkas style keratin diplodocus-like spines running along the back. Maybe there was something like that going on here. Maybe there were 2 sets of spines that became 1 set of spines just before the hip. As I mentioned, we do not know the exact length of the tail. We don't know how long the whip part of it would even be. We reason that it would have one. These are flagellocaudатans, which just means whip tails. They're sauropods with long whips on the ends of their tails. Based on Dicraeosaurus, the chevrons on the bottom of the tail, the bones that are just hanging off the tail vertebrae, would be as long or longer than the neural spines up top. So you would expect the base of the tail to have this sort of long isosceles triangle appearance. It's interesting that they chose to restore the whip with banding on it. You see that occasionally. I don't know if that's based on anything. There are dinosaurs that we've recovered with banding on their tails, and obviously plenty of other animals have them. I mean, iguanas have them, and iguanas actually use their tails as whips. Maybe that's where it comes from. But, I mean, it is a bit of a trope, but it's a good trope. It's visually interesting. There's a 2005 paper about sauropod feeding postures, And it's interesting because I think the posture of this toy is based on that paper. Having the tail parallel to the ground is good, but as of earlier this year, in 2020, the rest of this posture is called into question. Vidal et al. Took a close look at the sacrum, that is the part of the backbone that's in the hip, of Spinophorosaurus, and that prompted them to take a second look at basically all true sauropod, eusauropod sacra. They found that the sacrum is wedge-shaped when you look at it from the side. It's straight out where the tail connects, but it's angling up where the dorsal part of the spine connects. That means they think that the ancestral eusauropod was a high browser. It was angling the entire front of its body upwards. Now, this became way more pronounced in macronarians like Brachiosaurus, but in dicraeosaurids, where they're trying to go low again, they had to secondarily adapt back down. Now, the sacrum of Dicraeosaurus, which the researchers looked at, is not as wedged as Brachiosaurus. It's only about a 10-degree incline, but it corrects for that by having the dorsal vertebrae wedged the other way, which creates this gentle S-curve, which makes the overall dinosaur vaguely resemble the classic bell-curved sauropod back, but in the restoration that Vidal et al. Included, just kind of looks sullen. Now, is this applicable to Amargasaurus? We don't have the centra, we don't have the bodies of the vertebrae for Amargasaurus' sacrum. We only have the top parts. As far as I was able to tell from Salgado and Bonaparte's original figures, the dorsal vertebrae of Amargasaurus are wedging downwards the same way that Dicraeosauruses do, but the humerus, that is the upper arm bone, in Amargasaurus is longer relative to the femur than Dicraeosaurus's is. Like, it's still much shorter, but there's less of a difference there. Which would mean that if they had a Dicraeosaurus-like hunchbacked posture, it was maybe less pronounced, tentatively. So what can we say about the head that the spine was working so hard to bring down to its food supply? Well, we don't have a lot of the cranial material. We have the brain case and little else. So we restore the rest of it after Dicraeosaurus, and now partially after Bajadasaurus, which was described last year. There was some disagreement, at least in the restorations that I could find, as far as how big the head should be once you start getting out from the brain case. As of Bajadasaurus being described, because Bajadasaurus has a complete jaw, that allows us to have a better idea of what scale it would be. And in any case, the head on this toy is far too large. It's larger than even the largest reconstructions I saw. The chin on this animal doesn't really look like a dicraeosaurid chin. The bump on the bottom there would not be that exaggerated. I think the sculptor was just really concerned that we should know, hey, it's a relative of Diplodocus. But as of Bajadasaurus being described, we know for sure that the chin bump was, if you would even see it through the flesh, it would not be this pronounced. This toy's jaw is wrong in another respect. The back of the jaw on Dicraeosaurids was actually pretty far forward. This one is back behind the eye. It would be under or slightly in front of the eye, not at the back of the head like in this toy. And if we look at the head in dorsal view, it's very strange. The back of the skull, where the eye sockets are, was indeed the widest portion of the skull, but it was not this big wedge shape, and the eyes were definitely not on these weird little stalks, like what's going on this toy. It's somewhat hard to see, but the nostrils on this toy are actually sculpted in. They're just in front of the eyes. I think they might actually be further back than we would expect the nostril hole to be, the nares. Whereas we know that the nostril is usually at the very furthest forward point that it could be based on the bony nares, and some restore related animals like Apatosaurus with the nostril all the way at the front of the face, with a longer fleshy channel, possibly for honking or for its sense of smell, or maybe just having an inflatable structure there for display. The point is, the nostrils would not be back up towards the eyes. I can't tell, I don't think this toy has teeth. It doesn't appear to. If they tried to render dicraeosaurid teeth, it might be difficult at this scale. They had just simple pegs, like what you see in Brontosaurus or Diplodocus. They seem to have been feeding in the same method, where they crop and strip with a raking motion. Food seems to have been abundant for cropping and stripping. We have an incomplete picture of the Amarga Formation, but it was an alluvial environment, so floodplains with braided rivers, some swamps, some firmer soils, but lots of plants available. In early Cretaceous Patagonia, we have something of a pattern with large sauropods. In the Bajada Colorada Formation, we have a diplodocid, line cupal, and we have a dicraeosaurid, Bajadasaurus. In the Mulichinco Formation, we have a diplodocid that hasn't been named yet, and we have a dicraeosaurid, which is Pilmatuea. But then we get to the Amarga Formation, and we don't have a pair. We have two dicraeosaurids, Amargasaurus and Amarga titanus, tentatively. Amarga titanus at time of writing is a dicraeosaurid, but we don't have a diplodocid known yet. So we don't have a high browser to go with our medium-low browsers. I don't know what that suggests, but it's interesting. I keep insisting that this animal was a low browser, and the best evidence we have of that is the shortness of the neck. You've probably noticed already that as far as sauropods go, this is a really short neck. This is actually really good on the part of the toy sculpt. This is about the length that you would expect the neck to be. We have both fewer vertebrae making up the neck, and the vertebrae themselves are quite short compared to what we see in diplodocids. If we want to know what the habitual posture of the head and neck would be, there's a 2014 paper on the brain case anatomy. They found, among other things, that the orientation of the ear canal, as well as the shape of the first two neck vertebrae, the atlas and axis, shows that the animal was habitually holding its head muzzle down. Now that doesn't mean that it couldn't elevate its head. Taylor, Weddell, and Nash showed that even animals whose osteologically neutral pose for the vertebrae would indicate otherwise, they'll totally hold their heads in a really bendy posture if it means that they can look around at things. Now you might say, Stephen, these structures on top of the neck look like they would get in the way of it trying to raise up its head. I would flip that objection around. Instead of asking, what effect did the neck spines have on the posture of the neck, ask, did the posture of the neck require neck spines? It would seem that the miniaturization of the neck in dicraeosaurids caused them to have much longer forked spines than in their relatives. But why? What advantage do forks on vertebrae have? Bifid or bifurcated spines on vertebrae are an adaptation that shows up in a lot of sauropods and a lot of living animals. They seem to be an adaptation for bearing weights and loads on the end of the neck, or in Stegosaurus, on the end of the tail. Because if you have bands of ligaments on the ends of those neural spines, if you're moving that weight side to side, they'll just automatically pull it back into center once you stop exerting effort. It's a very energy efficient way to move around a large, or in the case of sauropods, long weight. However, Amargasaurus's neural spines lack the rugose attachment areas that you would expect if it had bands of ligaments there. So what gives? Schwartz and her co-authors thought that the ligaments were just entirely reduced or integrated into the supraspinal ligament, which is centered. Woodruff, by contrast, thought that the dicraeosaurids were starting to favor up and down movement, dorsoventral movement, instead of side to side, like in diplodocids, and that instead of unforking the vertebrae, they just made the forks longer. Schwartz and co-authors also found that the forks would support and enclose the supravertebral diverticula, which is a fancy word for air sacs. Diplodocids have these too. There's a big air sac on top of the vertebra in between the forks. But diplodocids have much more pneumaticized bones in their necks, so the air sacs can penetrate the bone much more than Amargasaurus, and their vertebrae are just longer. So it would seem that as dicraeosaurids shortened their necks, the air sac up on top of the vertebrae got taller to account for all of the loss of volume elsewhere. Now, Woodruff, by contrast, dissected some really specific cows called Ancole Watusi cattle. They have enormous horns on their heads, and as a result of having to move that giant weight around, have bifid neural spines on their necks. He has reconstructed a somewhat different cross-section of the neck. He has much more space being taken up by these huge bands of elastic ligaments and much less space being taken up by the air sacs. I'm somewhat unconvinced by Woodruff's reconstruction, which is much more like a cow than like a stem bird, which is what sauropods were. I was impressed to notice that this toy has the correct number of spines on its neck, with one exception. The first pair of spines on this toy is not in fact a pair. The spine on the axis is not actually forked, it's just one. There is a channel or fuller up the back of it, so it has kind of a U-shaped cross-section, but it is just one spine. So if you're going to restore it with sails, the sails need to converge at that first spine. I really don't know where the trope of having skin sails here originated. The original description has keratin-covered spines. They envision them as an adaptation for intraspecific combat, that is, settling disputes with other Amargasaurus. The earliest reconstruction I could find with sails was in a 1993 article by Dino Don Lesson, but it didn't have any details about what the reasoning was for having those sails. By the following year, Gregory S. Paul found it necessary to address this. He pointed out that the spines themselves are circular in cross-section. They're not flattened like you would expect in a sail structure, and they have tapered tips rather than broad tips. He compares the horns to an ibex's horns, where they point backwards anatomically, but they're still used forwards by just tilting the head down and back. He even speculated that they could clack them together to make audio signals to other Amargasaurus, which I don't... Sure, that's cool. Paul also argued that having a fleshy sail between the spines would limit the neck's flexibility, but that would really depend on the form that such a sail took. And to answer that, we look to Bailey in 1997. He had a monster of a paper that looked at neural spines in a bunch of dinosaurs and compared them to buffalo, and said that in a lot of cases, what we're looking at here is more like a muscular hump than a sail. But Amargasaurus didn't fit that paradigm. He considered it the only credible example of a crested dinosaur. He noticed that the spines are pretty similar to what you see in Dimetrodon, which is interesting because currently, Dimetrodon might not have the sails going all the way to the tips, and I've never seen a Amargasaurus restored quite like that. But even more interestingly, Bailey thought that a pair of sails is unlikely, because as I said, they're not forming this wide V. They're actually really close together, only a few centimeters apart. So he thought that it was this one giant pad on the animal's neck. Now that kind of arrangement would certainly limit the neck's mobility, and it would be difficult to say what its purpose would be other than display. But to return to Schwartz et al., the texture of the bone on Amargasaurus's spines is similar to the texture that we find on horn cores in living animals. That would suggest that they were covered in a sheath of keratin. You sometimes see this restored even with the ridges that you see on something like an ibex, which, again, no real evidence for that, but does look cool. But because the spines were also supporting those large air sacs, the keratin-covered or skin-covered portion would only be the upper 2/3 of the spine. So the fleshy portion of the sail with the sacs in it would be slightly higher in the middle of the neck than it is at either end of the neck. And while we're on the subject, this toy's spines are too straight. The ones nearing where the body starts are pretty good, where they're almost perpendicular, but the ones closest to the head should be much more raked back, which is more evidence that they would be covered in horn. So, If we're going to restore it with keratin horn sheaths, how long should those horns be? Well, Boreapelta is coming to the rescue. Brown published a paper where he did some regressions of extant animals' ratio of horn core to sheath, and he found allometry between those two. With very short horn cores, you have really short horns, as you might expect, but the longer the horn core gets, the longer the portion of the horn not supported by it gets. What that means for Amargasaurus is that the shortest spines, where they're only about 25 centimeters, would have a 30 to 50 centimeter horn, but then the longest spines, where they're 75 centimeters, would have a 135 to almost 2 meter horn. One reason that there's been so much debate over the form and function of Amargasaurus' spines is because it was the only sauropod that we knew of with such spines, until 2019 and the description of Bajadasaurus. This animal is most succinctly described as reverse Amargasaurus. It has really long neural spines on its neck vertebrae, but raked forward instead of raked backward. Interestingly, it's not the sister taxon to Amargasaurus. It's rather more basal, which means that having spikes on your neck projecting forward while your head is down was a viable defensive and/or visual deterrence across 15 million years in South America. What's tantalizing is that there's another dicraeosaurid from South America, Pilmatuea, which is in between, cladistically, Bajadasaurus and Amargasaurus, but the tops of the cervical vertebrae where the spines would connect are broken off. We don't know how long they would be. We don't know whether it would be like Dicraeosaurus, where they're pretty short and have ligaments attached, or if they would be really long, and we don't know if they're, I don't know. We've got Amargasaurus with them raked backwards. We got Bajadasaurus with them raked forwards. Maybe we're gonna find out Pilmatuea is like heart shapes. We've been assuming all this time, since it was described in the 20s, that Dicraeosaurus is the normal dicraeosaurid, but we've got Bajadasaurus and Amargasaurus and potentially Pilmatuea with these long neural spines. Did those evolve just twice as these weird adaptations in Bajadasaurus and Amargasaurus, or was this something that a lot of dicraeosaurids were doing? We don't know yet. One thing I do know is that I really want to see more art of Amargasaurus and Bajadasaurus where they've been browsing around, and so they have a bunch of leaves and branches tangled up in their neck horns. I think that would be a good art. But that concludes our look at the surprisingly not that out there Amargasaurus. Once you put it into its context as a dicraeosaurid, especially with more recent discoveries, suddenly a lot of its anatomy makes sense. And I want to thank you all for watching Your Dinosaurs Are Wrong. Please remember to like, comment, and subscribe, and we will see you next time. We would like to extend a special thank you to these individuals who have gone above and beyond to support this show. We could not have done it without you. Thank you.